Tonight, we're going to explore something genuinely strange happening on the moon. For most of modern space science, the moon was considered almost perfectly dry. It has no atmosphere to hold water, no clouds to move it, and no weather to return it to the ground. Sunlight should break exposed molecules apart, while the vacuum carries what remains away into space. Water should not survive there. And yet instruments are finding it in places where it should be impossible. Across parts of the sunlit surface, water molecules appear as temperatures rise, then weaken and disappear as the lunar day continues. Near the South Pole, something even stranger is happening. Inside craters that sunlight has not reached for billions of years, enormous deposits of ice may be locked into soil, colder than the surface of Pluto. The same moon appears to contain water that moves with the day, and water that has remained frozen since the earliest history of the solar system. That discovery changes more than our understanding of the moon. Those deposits could provide drinking water, breathable oxygen, and even the ingredients for rocket fuel, turning a handful of shadowed craters into some of the most valuable ground beyond Earth. By the end of tonight, you're going to understand how water survived on a world built to destroy it, why permanent darkness created the perfect place to preserve it, and why the strange activity near the lunar South Pole is changing where humanity plans to return. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. For most of the space age, the moon's dryness seemed beyond dispute. Every condition pointed toward the same conclusion. With almost no atmosphere, exposed water could not collect into clouds, fall as rain, or remain stable across the surface. Daylight heated the ground for roughly 2 weeks at a time, while solar radiation broke apart molecules and the vacuum allowed them to escape. There was no wind to carry moisture from one region to another, no active water cycle, no underground system regularly feeding the surface. Whatever water the early moon may once have possessed should have been stripped away billions of years ago. The samples brought home by the Apollo missions appeared to support that picture. Astronauts returned with hundreds of kilograms of lunar rock and dust, but nothing that looked like ice, damp soil, or a world still holding meaningful amounts of water. The moon seemed finished, dry, airless, chemically exhausted. That conclusion made sense because almost every place humans had visited lay under direct sunlight. The Apollo landing sites were chosen for visibility, communication, and safety, not because they represented every environment the moon contained. Near the poles, the geometry changes. The sun remains low against the horizon, and the walls of deep craters can block it completely. Some crater floors have remained in permanent shadow for billions of years, creating regions where temperatures fall so low that water arriving there may never receive enough energy to escape again. But the polar ice is not the only discovery challenging the old picture. Instruments studying areas exposed to sunlight have detected hints of something far less stable. Signals. Molecules that seem to appear on the surface as the sun climbs, then thin and fade as the day wears on, as if the ground itself were breathing. And down inside certain craters, in places where sunlight has never once touched the floor, something colder and far more permanent than a passing signal. Ice. Not scattered atoms drifting through the thin lunar exosphere and gone within hours. Ice that has apparently been sitting there, undisturbed, for a very long time. But here's where it gets strange. If sunlight and vacuum are supposed to strip water away, only two explanations are left standing. Either something on the moon keeps manufacturing water faster than the sun, and the emptiness can erase it, or something is holding onto it with an efficiency that borders on impossible. Both explanations point to the same address: the permanent shadows near the poles. Scientists have a name for those pockets. Permanently shadowed regions, PSRs for short, crater floors sunk so deep and sitting so close to the pole that sunlight never once crosses the rim to reach them. Natural cold traps, places cold enough to keep water ice from sublimating away, from turning straight to vapor and drifting off into space without ever passing through a liquid stage, for spans of time measured in the age of the solar system rather than a human life. No one is claiming a lake down there, or anything a person could scoop up with a cup. What the instruments are describing is closer to a very old, very well-hidden deposit, packed into ground that has never once seen the sun. So the dead, sealed, sun-scoured moon was never the whole picture. Not dry, not dead, not sealed shut after all. Water is hiding in the one place no one thought to look for it, hidden inside the coldest ground the moon has to offer, and sitting there still, decades after the first hints of it were quietly dismissed. That single fact rewrites the arithmetic of every mission that follows it. Why should a trace of frozen water buried in shadowed dirt matter this much? Because everything a crew needs to survive is heavy, and hauling it up out of Earth's gravity well is one of the most expensive things human beings have ever tried to do. Water means drinking water, kept alive without a single tanker launched from Earth. Split it apart and it means oxygen to breathe. Combine that oxygen with the hydrogen and it means rocket fuel, manufactured on site instead of shipped up at ruinous cost. A resource like that does not just support a future outpost. It makes one possible in the first place, turning a return trip to the moon from a one-way delivery of everything a crew will ever use into something closer to living off the land. And here is the cruel symmetry underneath all of it. The same shadowed ground able to sustain a base is engineered, by the plainest physics, to destroy one. The cold does not merely chill machinery, it seizes it, freezing joints and fluids that were never built to sit that far below zero. The darkness does not just dim the light, it removes cheap solar power entirely, the one source of energy every prior lunar mission has leaned on. And the dust scattered across that ground does not behave like dust on Earth. It behaves like glass powder, charged and clinging, ready to work its way into any seal or joint left exposed. Build nothing to withstand it, and the very ground that could feed and fuel a crew will just as quietly take their equipment apart. The prize and the trap turn out to share the same coordinates on the same map, which is the real reason the South Pole has become strategic rather than merely interesting. Draw a map of where the ice most likely hides, and lay it over a map of where missions actually want to land, and the two outlines nearly trace each other. Whoever plants the first working infrastructure beside those craters does not just win a scientific first, they shape what opportunities are left standing for everyone who arrives after them, quietly setting the terms before anyone else has even landed. The dead moon was never dead. It was holding something back. In the one place no one had reason to look for it. What took decades was not the water existing. It was believing the signal enough to go looking properly. Believing the signal had been the hard part. Explaining how anything frozen could survive down there for that long was the part that came next. The mechanism responsible has a name: sublimation, ice turning straight into vapor and drifting off into the vacuum, with no liquid stage in between. There is no meltwater on the moon, no puddle, no in-between state. Ice simply thins from the top, one molecule at a time, until eventually nothing is left. How fast that happens depends almost entirely on temperature, and the dependence turns out to be savage. At about 109 degrees above absolute zero, crystalline ice loses roughly 100 kilograms for every square meter of surface, every billion years. Spread that loss out and it comes to about 10 centimeters of thickness, gone across a span of time longer than complex life has existed on Earth. Effectively permanent. But warm that same ice by only 5 degrees to 114K, and the loss rate does not creep upward. It jumps roughly tenfold to about a meter lost per billion years. Put simply, a millimeter of surface ice sitting at 100k can survive more than 2 billion years. That same millimeter at 125k is gone in about 1,000. 5 degrees. That is the entire difference between a crater that keeps its ice for the age of the solar system and one that loses it in a geological blink. The physics is not forgiving. It does not average out or split the difference. It picks a side, hard, at a threshold most people would never think to look for. Modern cold trap science abandoned a single cut-off temperature for exactly this reason. A flat line at 110k turned out to be a poor predictor of anything. What actually defines a cold trap now is a loss rate, roughly 100 kilograms per square meter per billion years or slower. As a rough guide, about 110k, close to minus 163 Celsius, is the practical ceiling above which bare surface ice cannot last on geological timescales. Measure the shadowed floors themselves, and that ceiling stops being theoretical. Temperatures inside the deepest south polar shadows run from about 20k up to 120k. The single coldest spot ever directly measured anywhere in the solar system sits inside Hermit Crater near the North Pole at minus 248 Celsius, about 25k, recorded by the Diviner instrument aboard the Lunar Reconnaissance Orbiter as it passed overhead reading heat instead of light. Not merely cold, colder than Pluto. Pluto averages around 40k despite orbiting roughly 40 times farther from the Sun than the Moon does. A world 3 times closer to the Sun than Pluto, with no atmosphere at all to soften anything, and its coldest ground still wins. Burial pushes the tolerance further still. Ice sealed under a layer of loose soil, rather than left exposed on the surface, can stay stable up to about 140k, roughly 30 degrees warmer than bare ice could ever survive, because the covering blocks the direct route out into vacuum. Covering the ice sounds like it should smother it. It does the opposite. Burial is what saves it. The surface above that buried ice never sits still. Micrometeorites strike constantly, churning the top few meters in a process scientists call gardening, the same word used for turning over soil in a backyard bed. Gardening cuts both ways, much like a faucet filling a leaky bucket, where what is left behind depends on how fast the ice is being covered against how fast it is being dug back open or boiled away. It can protect ice by burying it deeper. It can just as easily destroy ice by exposing a pocket that had stayed sealed for eons. Because of that constant churn, nobody exploring these craters should expect a buried skating rink of clean, glassy ice sitting a few meters down. What is actually there is ice-bearing dirt. Ice mixed straight through the regolith, the loose broken rock and dust that blankets the entire moon, with some patches running as high as 30% ice by weight. The traps themselves are younger than the moon. About 2.1 billion years ago, the moon's axial tilt was nearly twice what it is today, closer to 3 degrees rather than the roughly 1.5 degrees it holds now. At that steeper angle, sunlight still reached almost every low corner near the poles, and almost none of the permanent shadow existed at all. Only in roughly the last 3.4 billion years did enough of that shadow appear for a real cold trap to begin forming. Even after the shadows appeared, they did not all turn cold on the same schedule. Cabeus, the crater where a later mission would go looking for ice directly, fell into permanent shadow only about 900 million years ago. Shackleton Crater has sat in darkness far longer, roughly 3.5 billion years, and yet it only grew cold enough to actually trap ice around 500 million years ago. Darkness alone was never enough. The temperature had to fall the rest of the way too. Inside the oldest, longest shadowed craters near the South Pole, more than 10% of the surface is now covered in ice, and the oldest shadows tend to be the iciest. That points towards slow accumulation, stretched across deep time rather than one dramatic delivery. an inheritance the South Pole has likely been quietly building for at least 1.5 billion years. Put the physics and the timeline together, and the opening paradox finally resolves. A world with no atmosphere and a sun-scoured surface should not be able to keep ice anywhere. Drop below about 110k, bury that ice a little deeper, and hold it there for a billion years, and losing it becomes the unlikely outcome, not the expected one. Here is the reversal sitting underneath the whole story. The same cold that would seize any unprotected machine on those floors. The same darkness that blacks out every solar panel. The same burial that would ruin almost anything else brought down there is the exact reason there is ice left to find at all. The hazard and the prize are not two different things sharing a coordinate. They are the same physics, looked at from two directions. What still is not settled is how the ice got there in the first place. Whether it arrived in one great delivery or gathered slowly, one faint addition at a time, across a billion years. Proving any of that, though, first required proving the ice was real, and that fight took far longer than the physics alone would ever suggest. The physics said the ice could survive. Whether it actually did survive was a different question, and answering it took the better part of 50 years. Starting with a result almost nobody in the West ever read. For most of the space age, the working assumption was that the moon is bone dry, baked by the sun, blasted by radiation, with no atmosphere to hold anything in place. It looked like a world with no way to keep water anywhere on it, ever. Here's what scientists believed at the time, and every hint that pointed the other way got measured against that belief first, and usually lost. In August 1976, a Soviet spacecraft named Lunar 24 touched down in Mare Crisium, drilled roughly 2 meters into the ground, and carried 170.1 grams of lunar core back to Earth, a sample small enough to sit in 2 cupped hands. Soviet researchers analysed it and published their findings in 1978. Water, they reported, made up about 0.1% of that core by mass. It should have been a landmark. Instead, it disappeared. The paper was written in English. It sat available in libraries the whole time. And still, no Western scientists cited it for more than 3 decades, while NASA's default assumption quietly filed the finding away as terrestrial contamination. Water assumed to have leaked in from an Earth lab bench rather than survived on the moon. Not lost, not disproven, simply unread. 2 space programs, 1 Cold War, and a result invisible to the side that would spend the next several decades searching for exactly what the other side had already pulled out of the ground. 18 years passed before the next real clue surfaced. In 1994, a joint mission between NASA and the Ballistic Missile Defense Organization sent a small spacecraft called Clementine into lunar orbit. Clementine ran an experiment called bistatic radar, bouncing a radio signal off the ground near the South Pole and reading how the signal came back. The same basic idea as an echo, except the echo carries information about what it bounced off. A 1996 analysis of that echo found a twist in the signal consistent with ice hiding somewhere in the shadowed terrain. 3 years later, in 1999, a reanalysis found that same twist showing up outside the permanent shadows too. In places, ice had no business being. The dispute never resolved either way, and it never would. Clementine's larger contribution turned out to be the map, not the radar. It charted the permanently shadowed craters themselves. Terrain the moon's shallow tilt keeps sealed in darkness without end, and raised a real possibility. Any water-bearing comet or meteoroid that ever struck nearby could have left ice, frozen solid on those pitch-black floors, sealed away the moment it landed. That single idea lit a debate that would run for more than a decade, and it turned a patch of empty-looking terrain into the most closely watched real estate on the moon. 4 years later, in 1998, a spacecraft called Lunar Prospector carried an instrument called a neutron spectrometer into lunar orbit. It cannot see hydrogen directly. Instead, it reads the neutrons that naturally leak out of the lunar soil as cosmic rays strike it, and hydrogen atoms drain unusual amounts of energy from those neutrons on their way out, leaving a signature behind like a fingerprint on the data. A dip where hydrogen sits, a rise where it does not. Prospector found that dip at both poles, hydrogen sitting somewhere beneath the surface, and this time, the signal did not fade under scrutiny. The numbers look real. On average, something like 100 to 150 parts of hydrogen per million buried under roughly 10 centimeters of dry soil, about the thickness of a hardcover book, standing on its spine, enough to imply hundreds of millions of tons of water ice at each pole. Later remodeling found that pole-wide average was hiding a much wider range underneath it, from as little as 200 parts per million in some patches to as much as 40% water by weight in others, pockets soaked far beyond anything the average number let on. For the first time, the case for polar water had numbers behind it, not just a single disputed sample and a disputed echo, but hydrogen is not water. That was the catch that would not go away. The same signal could just as easily point to hydroxyl, a related but different hydrogen compound made of hydrogen bonded to a single oxygen atom instead of two, or to something else entirely. A strong signal was not the same thing as an answer. Tantalizing. Still nowhere near proof. So NASA decided to force the question directly, the same way you settle an argument by striking a match, instead of guessing what the room smells like. In July 1999, controllers steered the spent Lunar Prospector spacecraft into the shadowed Shoemaker crater near the South Pole, diving in at about 1.7 kilometers a second, fast enough to cross 20 football fields in the time it takes to blink. Sealed aboard was a small capsule carrying the ashes of geologist Eugene Shoemaker. If real ice waited under that floor, the impact should have thrown a visible plume of water vapor into space, and telescopes across Earth turned toward the spot to watch for it. Nothing rose. NASA had rated the odds of catching a visible plume at only about 10% to begin with, so the silence was not entirely a surprise, and researchers pointed afterward to a mix of possible causes: poor targeting, a strike on bare rock, dry soil at the exact point of impact. No single explanation ever stuck, and the crater kept its answer to itself. A decade later, the pattern repeated almost exactly. In 2009, Japan's Kaguya orbiter, ahead of its own planned crash landing, aimed a camera sensitive to light about 1/10,000th, as faint as full daylight at the floor of Shackleton crater, straining to catch any glint of ice on bare ground. It found no visible ice. The team was careful about what that null result actually meant, and said so plainly. It ruled out ice exposed openly on the surface. It said nothing at all about ice buried or mixed into the soil underneath, and a camera, however sensitive, can only show what light reveals. 2 searches, 2 empty results. On paper, the South Pole looked dry after all. It was not empty. It was mist. The proof had simply been looking in the wrong place, at the wrong depth, with the wrong instrument. And the mission that would finally get all 3 right was only months away. That mission arrived within the year, and it began not in Washington or Moscow, but in India. 4 months after Kaguya's camera had come back empty, a different kind of instrument was already on its way to the same region. And this time, it was not looking for a glint of light on bare ground. On 14th November 2008, the Indian spacecraft Chandrayaan-1 released a small probe called the Moon Impact Probe from an altitude of 100 kilometers, nearly 10 times higher than a passenger jet ever climbs. The probe fell for roughly 25 minutes, aimed at the region near Shackleton crater, the same crater Kaguya had already searched by eye and found nothing. This time, the instrument was different. An onboard mass spectrometer named CHASE, a device that identifies molecules by sorting them according to their weight, the way a kitchen scale sorts ingredients by theirs, did not need to see ice glint in sunlight. It only needed to taste the air. Every 4 seconds on the way down, it drew in a sample of the moon's wisp-thin atmosphere and sorted what was in it. It found water molecules in that air, not inferred, not modelled, measured directly, the first such measurement since the Apollo missions ended decades earlier. But here's where it gets strange. The bigger surprise did not come from the falling probe at all. It came from an instrument still in orbit on the very same spacecraft. The Moon Mineralogy Mapper, known as M3, built to read the chemical fingerprints sunlight leaves behind when it bounces off different minerals on the ground. M3 found a hydration signature, a telltale dip in reflected light near 2.8 to 3.0 micrometers, and it turned up across the sunlit surface, strongest at the cooler high latitudes, not confined to the permanent shadows, spread across ground that faces the sun every single lunar day, on a world assumed too hot and too exposed to keep water anywhere near sunlight. The signal was thin, almost too thin to trust. The absorption implied a layer only about 0.09 micrometers thick, roughly a single molecular skin of water and hydroxyl, water's close chemical cousin, coating each grain of soil like breath, fogging a cold window. It was likely made and unmade continuously, hydrogen carried in on the solar wind, driving into the minerals to form it, sunlight and vacuum stripping it back away, a signal that should not have lasted and refused to sit still even while scientists were studying it. Whether any of that thin, restless sunlit coating ever drifted far enough to feed the deep, ancient reserve locked in the shadows was a real question, and it stayed unanswered. The two kinds of water, one skin deep and daily, the other buried and old, were related, but nobody could yet say how much one owed the other. Wait, that same week, in September 2009, 2 other spacecraft caught the identical fingerprint, and neither of them had been sent to look for it. The VIMS instrument aboard the Cassini probe, passing the moon years into a mission built for Saturn, and an infrared spectrometer on Epoxy, the retasked Deep Impact spacecraft, both recorded the same 3-micron hydration on the sunlit moon almost by accident, catching a signal nobody had asked them to find. All 3 results published together in the same issue of the journal Science. 3 separate instruments, built for 3 separate purposes, 3 separate missions. The same week, the same answer arrived at independently. Then came the hammer blow. On 9 October 2009, NASA drove a spent Centaur rocket stage, the emptied upper half of the rocket that had already done its job getting to space, about 2,300 kilograms, roughly the weight of a loaded SUV, into the permanently shadowed floor of Cabeus crater. It struck at about 2.5 kilometers a second, more than 7 times the speed of sound. Multiply that mass by that speed, and the arithmetic comes out to energy equivalent to about 2 tons of TNT. Enough force to level a small building, all released in an instant on a crater floor that had not felt sunlight or warmth in 1 billion years. A second spacecraft trailed 4 minutes behind, flying straight through the debris plume the impact threw up, reading the cloud with its own instruments before crashing into the same crater itself moments later, close enough behind to catch the plume before it settled back into darkness. The plume settled the question. Analysis published in 2010 found water ice in that debris at 5.6%, plus or minus 2.9% by mass, with up to about 155 kilograms of water vapor and ice sitting inside the instrument's field of view, about as much as 2 grown adults weigh. This was not a whisper of a signal buried in statistical noise. It was a measured percentage, with an honest margin of error attached, pulled directly out of a debris cloud thrown up from ground no sunlight had ever touched. Alongside it sat a wider chemical inventory pulled from the same buried soil: light hydrocarbons, hydrogen sulfide, sulfur dioxide, ammonia, carbon dioxide, a cocktail of compounds no one had ever measured there directly before, evidence that the shadowed floor was not simply icy but chemically rich, holding onto far more than water alone. At 5.6% by mass, the shadowed floor of Cabeus was roughly twice as wet as ordinary soil in the Sahara Desert. Not a trace, not a maybe, twice as wet as a desert, buried in permanent dark, on a world people had spent 50 years calling dry. The hydrogen that Lunar Prospector had glimpsed a decade earlier, the signal too ambiguous to settle anything on its own, the signal that could have been hydroxyl or something else entirely, was now confirmed as exactly what it always might have been: frozen water, sitting where the physics had said it should. Maps of confirmed ice followed at both poles, and the pattern was not scattered or random. It sat concentrated in the coldest, darkest floors that had never once seen sunlight. The very ground the sublimation math had already marked as capable of holding ice for billions of years without meaningful loss. 2 lines of evidence, one built from a falling probe and an orbiting spectrometer and a rocket stage driven into a crater, the other from decades of patient physics worked out on paper, had converged on the same coordinates without either side setting out to prove the other correct. The case that opened with an unread Soviet paper in 1976 closed within a single year, 2008 into 2009, not with one clean answer, but with 5 converging ones. A probe that tasted water in the thin lunar air. A mapper that found a molecular skin of it in daylight. 2 independent spacecraft that confirmed that same skin the same week. And a rocket stage that drove into a shadow and came back with a number. What had been suspicion for 50 years, filed away, disputed, searched for, and missed twice, was now a fact with a location, a depth, and a percentage attached to it. The next question was no longer whether the water was real. It was how much of it there actually was, and what that much might actually be worth. The shadowed polar regions could hold on the order of 600 million tons of ice, roughly half the volume of Lake Travis, the reservoir lake outside Austin, Texas, or enough to fill more than 240,000 Olympic swimming pools packed into craters that never see the sun. Almost all of it sits locked in the same cold, dark ground the earlier searchers had already mapped. The very floors that had spent 50 years looking as empty as the rest of the moon. That is not a small number dressed up to sound big. It is a reservoir on the scale of a small freshwater lake, sitting frozen and buried on a world every prior generation had written off as sealed and dry. And it did not arrive as one clean measurement. It arrived the way most real numbers in science do, as 3 separate estimates from 3 separate missions, made years apart, that had to be reconciled rather than simply read off a single instrument. Getting to that figure took 3 separate missions, and on the surface their numbers do not agree with each other. Lunar Prospector's neutron data first implied about 300 million tons back in 1998, a first rough sketch built from the same buried hydrogen signal that had once been too ambiguous to prove anything at all. A refined pass at that same data later that year jumped the estimate to about 6 billion tons combined across both poles, 20 times higher than the original number, from nothing more than a second look at data already in hand. Then, in 2010, the mini-SAR radar riding on Chandrayaan-1 found ice signatures inside more than 40 craters near the North Pole, each between 2 and 15 kilometers across, and put the North Pole alone at a minimum of 600 million tons. 3 numbers, 3 missions, 3 very different totals. Not a contradiction. Different instruments, different assumed depths, different patches of ground measured, each one reading the same buried reservoir through its own narrow window. Stack them side by side, and they do not cancel each other out. They narrow a picture nobody had finished drawing, closing in on the same order of magnitude from three unrelated directions, rather than arguing with the mission before it. The moon is not bone dry even outside those shadows. Trace water was found migrating loose across the sunlit ground itself, and in 2019, an ultraviolet spectrograph aboard the Lunar Reconnaissance Orbiter, an instrument called LAMP, caught it moving. Molecules cling to the soil through the cold night and most of the following day, then work loose again near local noon, hopping to a colder patch of ground or drifting briefly into the moon's exosphere, its whisper of an atmosphere, before settling back down as the temperature falls. It happens more at high latitudes than near the equator, a slow migration toward the poles playing out one lunar day at a time. Then, in October 2020, NASA's SOFIA, a telescope flown inside a modified aircraft above most of Earth's own atmosphere, confirmed something stronger. At Cabeus crater in full daylight, SOFIA detected actual molecular water, not just hydroxyl standing in for it, at a concentration of 100 to 412 parts per million. Picture a 12-ounce bottle of water poured into a cubic meter of soil and spread through it evenly. NASA framed the number plainly, about 100 times drier than the Sahara. On the sunlit face of an airless, radiation-blasted world, where a bare water molecule should not survive the day, there it was anyway. Where all of it came from is not one story, but several running at once. Ancient comets are one candidate delivery method. Asteroids are another. Micrometeorite bombardment, the same slow hail that gardens the surface everywhere on the moon, is a third. And some of it may be primordial, water present since the moon itself formed, never delivered from anywhere at all. No one source has been ruled in or ruled out. The honest answer is that the reservoir is probably a mix of all four, layered in over billions of years by processes that left no separate signature behind to tell one contributor from another. The solar wind route is the strangest of the four. Protons streaming outward from the sun strike the ground, pick up stray electrons, and become hydrogen atoms. That hydrogen works its way into the soil and bonds with oxygen already locked inside the rock-forming minerals there, building hydroxyl and water molecule by molecule out of sunlight and stone. Laboratory work suggests bombardment alone is often not enough, that the reaction likely needs periodic heating from the sun to finish forming water rather than stalling as loose hydroxyl. Most of what survives long-term, though, is not this daily churn. It is old ice, buried in permanent shadow, water that wandered poleward over billions of years, and fell into ground too cold and too dark to ever let it go again. The picture did not hold. A sunlit, airless radiation-blasted surface should erase a water molecule almost instantly. No shelter, no atmosphere to slow anything down. And yet SOFIA found water sitting right there on Cabeus's sunlit face. Not annihilated, preserved. The same micrometeorite impacts that should be destroying the ground are fusing water into tiny beads of glass that seal it inside. The same sandblasting solar wind that should be stripping molecules away is the very process manufacturing the hydroxyl in the first place. The destroyer, again, moonlighting as the protector. For scientists, that history, comets and asteroids and sunlight-made chemistry all converging on the same buried ice, is the real prize. Every one of these polar craters is a time capsule, holding not just water, but a record of how water has moved through the whole solar system since before the moon had finished cooling. Read carefully enough. A single scoop of that buried ice could carry the signature of a comet that broke apart billions of years ago. alongside water built molecule by molecule out of nothing but sunlight and rock the following week, geologically speaking. For anyone planning to go there, the prize is simpler. Explorers have taken to calling it space oil. Split the water into hydrogen and oxygen and it becomes rocket fuel and breathable air. Leave it whole and it becomes drinking water and life support. Either use replaces cargo that would otherwise have to be launched from Earth at ruinous cost, dead weight fought free of gravity just to be carried back down again somewhere else, mission after mission for as long as anyone keeps going. That is what turned 600 million tons of buried ice into a fuel depot and a base camp at once, and why whoever learns to actually pull water out of that ground first gains a running head start on everything else done in deep space afterward. But the same cold, the same dark, and the same violent history that built and hid this reservoir for billions of years were never going to simply step aside for whoever came looking to collect it. That cost starts with geometry, and geometry alone explains why some ground on the moon has stayed dark for longer than complex life has existed anywhere. The moon leans only about 1.5 degrees on its axis, a tilt smaller than a picture hung slightly crooked on a wall, and that tiny lean is the whole reason the sun never climbs high enough at the poles to look into certain crater floors. Tall rims throw permanent shadow across the ground below, and inside that shadow nothing changes, season after season, because there is no season left to change it. No sunrise has ever touched some of that ground. Not once. Not for millions of years running. Permanent shadow does not even require standing at the pole itself. It can begin as far out as about 58 degrees latitude, and roughly 50 such shadowed patches sit mapped in the band between 58 and 65 degrees in each hemisphere, stacked on top of the deeper, larger shadows closer to the poles themselves. To walk into one of those floors is to walk into a cave that never had an opening. At every reading, every step, every measurement has to be taken by lamp or by sensor, because there is nothing else to see by. No ambient glow, no reflected earthlight worth trusting. Nothing but whatever a machine carries in with it. That single fact carries hard practical costs. Solar panels are dead weight in permanent shadow, useless the moment they cross the shadow line, which rules out the cheapest form of power available anywhere else on the moon. Navigation and construction, ordinary tasks almost anywhere else on the lunar surface, become exercises carried out entirely blind, guided by radar and by memory of a map rather than by sight. Even communication grows harder, because a flaw deep enough to hide from the sun is often deep enough to hide from a straight radio line back to Earth as well. So relays have to be planned around terrain that was never meant to be crossed. Darkness alone would be hazard enough. Cold makes it worse. How cold could a shadowed crater actually get? A heat-sensing instrument called Diviner, riding aboard NASA's Lunar Reconnaissance Orbiter, has spent years reading the temperature of these floors from orbit, and in the coldest shadowed craters its midwinter night readings run down near 26 Kelvin, about minus 247 degrees Celsius. NASA's own summary states it more bluntly still, readings below minus 410 degrees Fahrenheit, 26 Kelvin. Not far from the lowest reading this story has already touched, colder still than Pluto itself, a world that sits roughly 40 times farther from the sun than the moon does. Cold enough that liquid nitrogen, the everyday coolant that boils at 77 Kelvin and is used routinely to flash freeze food and preserve tissue on Earth, would not boil at all if poured onto that ground. It would freeze solid on contact, turning to slush and then to ice on floors already dozens of degrees colder than nitrogen needs just to stay liquid in the first place. The swing across a single ordinary lunar day only sharpens the contrast. At the equator, daytime temperatures climb past 250 degrees Fahrenheit, hot enough to have boiled the thermometer measuring it, and by night, that same ground falls to nearly 208 degrees below zero, well past the point where dry ice stays solid. That is already a swing most of Earth's weather never comes close to. Even it never approaches the permanent floors. Earth's own coldest recorded temperature, set on the high Antarctic plateau, sits somewhere between about 89 and 98 degrees below 0 Celsius, a figure already hard to picture standing in. These lunar floors run roughly 150 to 160 degrees Celsius, colder than that. The gap is wider than the entire recorded range of Earth's climate, coldest pole to hottest desert, folded into the single difference between an Antarctic winter and one shadowed lunar crater. At that kind of cold, ordinary matter stops behaving the way it behaves anywhere else. Soil packs down hard as stone, no longer loose enough to dig with an ordinary scoop. Fuel and unprotected electronics freeze almost the instant they are exposed. Circuits going dead before a warning light could even register the drop. Metals and plastics turn brittle enough to crack under stress. They would shrug off at room temperature. A jolt that would only dent equipment elsewhere can shatter it here. Lubricants gum solid inside bearings, and battery fluid stops flowing at all, which means the parts of a machine built to move simply stop moving. And there is no waiting it out. A normal lunar day and night each run about 1475 Earth days, roughly 2 work weeks of sunlight, followed by 2 work weeks of dark, and ordinary landers elsewhere on the moon are built around that rhythm, shutting down at dusk and waiting out the 2-week dark for the sun to climb back into view. Inside a permanently shadowed crater, the sun never climbs back into view. Not a 2-week wait, not a season. Permanent. Hibernation is not a survival strategy on that ground. It is a slow way to die. Batteries bleeding out with nothing coming to recharge them, and no dawn anywhere on the horizon to wait for. The floors may be strange in ways that have nothing to do with temperature at all. Without a single sunrise to warm and cool the ground in a daily rhythm, and without the charging that daylight ordinarily drives across the rest of the lunar surface, these floors may hold their soil in physical states nobody has directly measured yet, denser or looser, or bound together in ways ordinary lunar ground simply is not. No lander has ever drilled deep into one and reported back exactly what it found. So for now, this remains an educated guess rather than a settled fact. One more unknown, stacked on top of the cold and the dark. What has been measured, though, is where the confirmed ice actually sits. It pools precisely in the coldest, darkest, most permanently shadowed ground on the moon. The same floors that freeze equipment solid, swallow sunlight whole, and strip away the one survival trick that works everywhere else nearby. The ground most capable of killing a mission outright is the very ground holding what the mission came there to find. Surviving long enough to reach it, let alone stay, is a different problem entirely, and it does not begin with the size of the rocket. If there is no dawn to wake up to, a machine has to carry its own warmth, and the answer turns out to be surprisingly small. Solar power is worthless the instant a rover crosses into permanent shadow, panels drawing nothing from a sky that never lightens. Batteries fare no better on their own. They can bridge a short gap in sunlight, but nothing on board can store enough charge to outlast a night measured in years rather than hours. So the real problem at the poles was never power. It was heat, and heat is a different problem entirely. One that no amount of extra solar cells or extra battery cells actually fixes. It gets solved instead with something that fits in a closed hand. The workhorse solution is called a radioisotope heater unit, a sealed lump of decaying plutonium-238 that simply gives off warmth hour after hour, year after year, with no sunlight required, no battery to drain, and no moving part to seize or wear out. The physics inside it is almost embarrassingly simple. Plutonium-238 sheds about 0.57 watts of heat for every gram it contains, just from decaying quietly inside its shielding, no reaction to trigger, and nothing to switch on. A standard 1-watt unit needs only a few grams of that fuel to work, and once wrapped in its protective casing, the whole heater masses around 40 grams. Something you could close your fingers around. Something that outweighs a few coins, but little more. And unlike every solar array on the moon, it never once needs to see the sun to keep working. The Soviets proved the idea decades before anyone thought to test it on purpose. Lunar-1 landed in 1970 carrying a polonium-210 heat source, keeping its sealed electronics above freezing through nights near minus 150 Celsius, cold enough that no ordinary Earth freezer comes close. It was designed to operate for 90 days. Nights near minus 150 Celsius. Designed for 90 days. It ran for about 322, well past 3 times its planned life. The little heater still quietly decaying long after engineers on Earth had stopped expecting to hear from it. Lunar 2 managed roughly 4 months before a heat-related failure, dust fouling its thermal control and ending the mission early. But the lesson from both rovers held regardless. A small heat source, kept running, buys years instead of weeks. China's current rover proves the same lesson today, decades later. The Chang'e 4 lander and its Yutu-2 rover have sat on the moon's far side since January 2019, carrying a radioisotope heat source built through a Sino-Russian collaboration that keeps their subsystems warm through far-side nights, cold enough to liquefy oxygen from the air, while solar panels handle the easier job of daytime power. Neither rover is unusually advanced. What keeps them alive, year after year, is the same small principle Lunar carried in 1970. Night after night, the heater does the part sunlight simply cannot. But here's where the lesson turns sharp. India's Chandrayaan-3 lander and rover reached the moon only months earlier, in a landing widely celebrated as a triumph, and both machines worked exactly as designed through their planned mission. But they carried no radioisotope heater at all, running on solar power and batteries alone, the same combination that fails everywhere permanent shadow reaches. In early September 2023, with the 2-week lunar night closing in, mission controllers put both to sleep before nightfall, leaving the receivers listening for a signal on the expected wake-up date, 22nd September 2023. Not a malfunction, not a lost signal. Silence. Neither one ever answered. They never woke up. The rocket had worked. The landing had worked. The science had worked. What was missing fit in a closed hand. Even with a working heater, cryogenic cold finds other ways in. Ordinary bearing oils and greases freeze solid at these temperatures, and thermal mismatch between materials warps shafts and degrades seals until bearing simply seize. A jolt that would only strain a motor elsewhere can lock it here entirely. A wheel motor that turns freely in an Earth lab can become dead weight after one cold enough night. Engineers answer this with special steels, alloys like 440C stainless, and with fluorinated lubricants formulated specifically not to freeze or turn brittle in the dark, the cryogenic equivalent of running an engine without oil and expecting it to keep spinning anyway. None of it is glamorous. All of it is the difference between a rover that turns its wheels on day 300 and one that does not. And even careful engineering is working from an incomplete map. The coldest ground of all may not be the broad-shadowed floors already charted from orbit, but tiny pockets called micro-cold traps, shadow patches cast by a single rock or a shallow dip, sometimes only a few centimeters across. Diviner reads temperature from orbit at a resolution of roughly 200 to 250 meters, a footprint the size of several city blocks, far too coarse to resolve a shadow smaller than a boulder. Models suggest these unseen pockets could add another 10 to 20% more cold trapping ground than the orbital maps already show. Some of the coldest, most hardware-hostile terrain on the moon has never actually been measured from anywhere. It can only be guessed at, modelled and remodeled, until a machine finally sits on top of one and reports back what it actually finds there. Keeping a machine alive through the freeze, though, only solves half the puzzle. It still has to reach ground worth surviving on in the first place. And that ground turns out to be almost as scarce as the cold is extreme. The ground worth surviving on has to satisfy two demands that look impossible to meet at once. It needs to sit close enough to reach the ice locked away in permanent shadow, and it needs enough sunlight to run a base on ordinary solar power, to charge batteries, split water, and keep instruments warm without burning through a heater's limited fuel. Ice lives in the one place light never touches. Power lives in the one place ice cannot survive. Put a base in the dark and it starves for sunlight. Put it in the light and it is stranded a long, difficult haul from the resource it came to use. On paper, no single patch of ground offers both. The moon's own geometry breaks the deadlock. Its axis leans only about 1.5 degrees, the same near upright tilt already responsible for the permanent shadows themselves, and on a handful of high ridges near the South Pole, that same tilt works the opposite way. The sun never climbs high there, but it also never fully sets. It skims the horizon in a long, shallow circle, keeping certain crests lit almost around the clock, while the crater floors a short walk downhill stay black without pause. The numbers back up how rare that is, and how good. A point near Shackleton's rim sees sunlight roughly 240 days out of every year, more than 8 months, with its longest single stretch of continuous darkness lasting only about a day and a half, not much longer than a weekend. Several other ridge points hold illumination between 81 and 90% of the year, and two of them, only about 8 kilometers apart, add up to a combined 94% between them. The best studied stretch of high ground, a roughly 14-kilometer span linking Shackleton's rim to De Gerlach crater, and known simply as the Connecting Ridge, averages 77 to 88% illumination, with its single best points reaching 92.3% lit at a mast height of 2 meters and 95.66% at 10 meters. Climb a little higher and the sun finds a little more of you. These peaks are calm as well as lit. Where the equator's wide swing, already described, can reach as low as minus 274 degrees Fahrenheit and as high as 230, close to the boiling point of water, the illuminated ridges barely move, holding steady in a narrow band between about minus 22 and minus 60 Fahrenheit. Cold, but a cold an ordinary heater can manage without strain. The moon is supposed to be a world of violent extremes, one patch scorching past the boiling point while ground a few miles off freefalls toward the coldest measured temperature in the solar system. Not these ridges, not this ground. Steady, month after month, because the sun never really leaves it. That steadiness is the setup. Here is the turn. Total every one of these lit slivers, every ridge and crest and crater rim, anywhere on the moon, that qualifies as nearly continuously sunlit. And the sum comes to only about 1 square kilometer, an area a person could walk across, edge to edge, in well under 15 minutes. The permanently shadowed ground it borders covers roughly 1,030 square kilometers at the North Pole, not far off the entire land area of Hong Kong, and about 2,550 square kilometers at the south, close to the size of the country of Luxembourg. The ice outmasses the safe ground beside it by roughly 1,000 to 1. That ratio is the whole story folded into 2 numbers. The resource itself is scarce. The safe ground beside it is scarcer still, by 3 orders of magnitude, and what remains comes in pieces small enough to count on 2 hands. Only about 4 major illuminated ridges lie within 15 kilometers of the pole, and each one is an island in literal fact, no more than a few hundred meters across, bounded on every side by permanent night. NASA's own image captions have taken to calling them exactly that: islands in the dark, small crests of daylight, standing inside an ocean of eternal shadow that stretches for thousands of square kilometers around them. The next candidate beyond those four, Malapert Mountain, sits roughly 122 kilometers out, farther than most people could cover on foot in a single day. From a ridge like the connecting ridge, though, the distances that actually matter shrink fast. Astronauts on foot could reach several shadowed craters within a traverse of about 2 kilometers, a walk of well under an hour, close enough that the island and the ocean around it sit in the same short afternoon. NASA has built its plans around exactly these slivers. Candidate landing regions carry the names of the ground itself: Peak near Shackleton, the connecting ridge, the rims above de Gerlache and Nobile Crater, each chosen for the same two reasons: sunlight that barely quits and shadowed, ice-sparing terrain within easy reach. And the shadows those ridges border are no longer entirely hidden from view. ShadowCam, flying since December 2022 aboard South Korea's Danuri orbiter, reads about 200 times more faint light than the camera aboard Lunar Reconnaissance Orbiter ever could, and it photographs the flaws of permanent shadow by the dim glow scattered off their own sunlit walls. A dark basin stitched directly to a blazing rim, the safe ground and the hidden ice framed in the same single image. Which sliver of that thin, bright margin becomes the site of an actual base is still an open question, and not a stable one. Modeled illumination shifts by several percentage points, depending on how tall a mast or an antenna is assumed to stand, and even the map of finalists keeps changing. NASA's own shortlist has already moved once, the connecting ridge among the names that dropped off the agency's updated plans by late 2024, a reminder that a list this short can rearrange itself before a single boot ever lands. The safe ground is found. What waits inside the shadowed ground it borders, the actual texture and chemistry of the ice itself, is a separate question, and a stranger one. Walk down off that ridge into the shadow itself, and the ground underfoot stops behaving like ground anywhere else on the moon. Sunlit soil bakes and cools every 2 weeks. A slow hammer that packs its grains tighter against each other with every cycle, over billions of repetitions, until the surface settles into something close to firm. The shadowed floors never feel that hammer. No sunrise ever arrives to expand a grain. No sunset ever arrives to let it contract and settle back down. So the soil stays as loose as the day it first came to rest, undisturbed for as long as the shadow itself has stood. Far ultraviolet measurements put the porosity of that shadowed regolith at around 70%, almost double the roughly 40% typical of soil that still sees the sun. Scientists call the result a fairy castle structure, a lattice of grains touching at only a few points each, closer to snow that fell overnight and has never been walked on than to sand packed firm on a beach. Put a boot on that ground, and it would not feel like standing on rock. It would feel like standing on something closer to ash. That fragility left a fingerprint the moment something actually struck it. When the spent Centaur stage hit Cabeus crater in 2009, the flash of the impact arrived late. It took about half a second longer than models expected to flash at all, and nearly 7/10 of a second longer to reach peak brightness, roughly the pause between one heartbeat and the next, stretched out and made visible. Scientists eventually read that lag as porous ground, swallowing the blow instead of throwing it back, the way a mattress absorbs a dropped weight, where a floorboard would just crack. The impactor's own hollow shape complicated things further, kicking up a plume in 2 parts, a low curtain of debris, and a taller jet rising above it, which blurred the expected signal even more. Even the way this ground gets hit does not behave the way engineers had modelled. Buried inside that plume was the number the whole case had been waiting for. Water ice at 5.6% by mass, give or take 2.9% in the first analysis. A later look at the same debris put it closer to 6.3%. Not a contradiction so much as the same crater measured twice, landing on a working range of roughly 3 to 9% either way. Real ice, but nowhere near a pure deposit. Whether that small gap between the two readings reflects genuine patchiness in the floor itself, or simply two different ways of reading the same faint plume, is a question the data still cannot answer on its own. The cold does more than trap that water. It sorts an entire pantry by temperature. Sulfur stays locked in place until about 202 Kelvin. Water holds until about 107. Ammonia lets go around 66. Carbon dioxide clings on only to about 62, a mere 10 degrees or so above the coldest anything in this story has been measured to reach. Only the very coldest floors hold onto carbon dioxide and ammonia at all. Ordinary water ice survives across a far wider stretch of shadowed ground, which is exactly why water dominates the inventory even where the rarer volatiles cannot last. The Cabeus plume carried the whole mixed pantry at once anyway. Light hydrocarbons, sulfur compounds, carbon dioxide, and fainter traces of hydrogen, carbon monoxide, calcium, mercury, and magnesium. A floor stocked less like a single freezer and more like a pantry with its shelves set at different temperatures, each shelf holding only what that particular cold can keep. It would be easy to picture all of this as a reservoir, a lake of frozen water sitting under a thin lid of dust, waiting for a drill to strike it. That picture is wrong. LRO's lamp instrument, reading starlight bounced faintly off the dark floors, found exposed frost covering only about 0.3 to 2% of the ground it could see. Wider mapping tightens that further still. Surface ice occupies less than about 11.5% of the cold-trapping ground inside any given crater, and across every mapped cold trap studied, only around 3.5% show any exposed ice at all. Not a lake, not even a pond. A scatter of patches thin enough to miss from most angles entirely, hidden inside ground already hidden from the sun. What hides below the surface offers a little more hope, at least in places. At Cabeus, L-Cross detected ice roughly 6 to 10 meters down, something like 2 or 3 stories beneath the floor. Modelling tied to crater age suggests the oldest, most poleward floors may hold ice columns near 20 meters deep, about the height of a 6-story building buried straight down, while younger craters, cold traps for a much shorter span of the moon's history, carry less than half that. Depth, it turns out, is its own kind of clock. Even a single handful of that buried ice is not one thing. Micro-CT scans of icy regolith reveal 3 separate textures tangled together in the same sample. Thin bridges of ice cementing grain to grain, loose ice filling the pockets of space between them. A fine frost simply plated onto the outside of each grain from vapor. 3 ways of being ice, occupying the same few centimeters of ground, and no single tool built to extract one of those forms is guaranteed to work on the other 2. Even that picture comes with a caveat worth holding onto. Most of what is known about how those 3 textures arrange themselves still comes from simulated lunar soil, mixed and frozen in laboratories on Earth, not from a sample pulled out of an actual shadowed crater. So the true layout underground remains a model, not yet a measurement. So what does a future engineer actually find when the drill finally goes in? Not a well. None of this looks like a well waiting to be tapped. It looks like ore, low-grade ore, dirty ice cementing together grains of abrasive dust, patchy at the surface, buried more often than not, tangled through 3 different textures wherever it turns up. The true scale of what else sits down there, the bulk carbon dioxide, the methane, the sulfur, is still not really known, because the entire inventory of ground larger than most countries rests on one impact site, and a handful of instruments are looking down from orbit rather than a single boot or drill bit that has ever actually touched it. Getting that ore out and getting it out clean would turn out to depend on a hazard already quietly on the move above that same ground. Fine, abrasive dust that refuses to stay where gravity puts it. That abrasive dust does not stay where it settles, because the ground itself is not neutral. Sunlight and the solar wind leave a charge behind wherever they touch the surface, and the sign of that charge depends entirely on whether the ground faces the sun or hides from it. Sunlit soil charges positive, ultraviolet light and X-rays knocking electrons clean off the grains in a process called photoemission, the same principle behind an old-fashioned photocell. Shadowed soil charges the opposite way. With no sunlight to strip electrons back off, the electrons raining in from the solar wind simply pile up, and the ground drifts negative hour after hour with nothing to discharge it. It is the same effect, at a vastly larger scale, that leaves a sock clinging stubbornly to a shirt pulled fresh from a dryer. Except here, the whole exposed half of the moon does it at once. One side gathering positive charge, the other negative, never neutral, always trading charge with the space around it. This video opened with a claim worth revisiting now that the mechanism is on the table. Hundreds of thousands of volts, the shadowed surface supposedly holding a charge close to a bolt of lightning waiting to happen. Wait. The measured number is nowhere near that. Under normal conditions, the floor of a permanently shadowed crater sits only a few hundred volts negative relative to the sunlit ground around it. Models of Shackleton's own leeward wall put it near minus 175 volts, a charge smaller than the static built up walking across a carpet in winter, the kind that snaps between a fingertip and a doorknob at several thousand volts. Only during rare events, when the moon swings through the long magnetic tail trailing Earth for a few days each month, or when a solar storm hits, does that potential spike into the low kilovolts, and even then it settles back down within days as the moon moves clear of the disturbance. Thousands of times smaller than the popular figure, not a bolt of lightning. A doorknob spark, and only occasionally even that. Modest voltage does not mean nothing happens. The real activity concentrates at the terminator, the moving line where day gives way to night as the moon slowly turns. The same slow rotation already described. Sunlight retreating on one side while darkness retreats on the other. There, the electric field can exceed 500 volts for every centimeter of ground, strong enough on its own to lift charged grains into the air, and where the local terrain breaks the surface into neighboring patches of opposite charge, the field crowds even higher, into the thousands of volts per centimeter. It is a narrow band, but it is where the action happens. Astronauts and instruments have already caught the result. Between 1967 and 1968, 3 SOFIA landers, SOFIA 5, 6, and 7, each photographed a faint glowing line low on the western horizon, just after sunset. Apollo 15 and 17 crews reported the same thing years later from orbit. A glow at sunset, and thin columns of light before dawn. The explanation settled on sunlight scattering forward through a thin, short-lived cloud of grains roughly 10 microns across, a tenth the width of a human hair, lofted off the ground by the terminator's field, and drifting for a few fleeting minutes before settling again. But the picture refused to stay tidy. NASA's Lady Orbiter, built specifically to study the lunar dust environment, recorded roughly 140,000 individual dust impacts during its mission, and used them to weigh the surrounding cloud. Its total came to only about 120 kilograms, no heavier than a large vending machine spread across the entire volume around the moon, and sourced mainly from ordinary micrometeoroid bombardment, rather than electrostatic lofting. That is roughly 100 times too thin, to explain the brightness Apollo's cameras actually recorded. The classic high-altitude dust cloud that astronauts and surveyor cameras seem to see has never been confirmed by a spacecraft built to measure it directly. Whatever produced the glow those crews watched from orbit, it left barely a trace for Lady to find. Only the finest grains lofted all, generally under a single micron, forming a low drifting belt that shift position as the sun's angle changes through the lunar day. Size does not limit charge though. A single grain no wider than a human hair, about 100 microns across, can carry more than 100,000 excess electrons, the same pull that makes a balloon, rubbed against a sweater, drag strands of hair upright and toward it, scaled down to grains instead of hair, and volts instead of a party trick. And charge does not fade quickly once it accumulates in the dark. On the sunlit day side, a grain discharges in about a millisecond, faster than a blink. Inside a permanently shadowed crater, starved of the sunlight that would normally bleed the charge away, that same discharge can take hundreds of seconds instead. Several minutes for a single grain to let go of what it is holding. The consequence loops back to where this whole account began. Charged dust drifts slowly from the lit ground toward the dark, nudged along by these fields, and settles into the same permanently shadowed craters that have been quietly hoarding water for billions of years. Much like the water, the dust finds its way into the cold and stays there once it arrives, drawn toward the same addresses by forces that have nothing to do with each other, and everything to do with where the shadows happen to fall. That drift looks almost gentle from orbit, a slow electrical sorting of fine material into the dark. What that same dust does once it reaches a human lung is not gentle at all. Apollo already knew that. All 12 astronauts who walked on the moon came home with the same complaint: sneezing, congestion, a raw throat, eyes that watered for hours, sometimes days after the helmet finally came off. Mission doctors filed it as a curiosity and gave it a name almost too gentle for what it turned out to be: lunar hay fever, as if the moon had pollen drifting somewhere across its surface. Nobody treated it as urgent at the time. Not a curiosity. A warning nobody heeded. Everyone who ever walked there had it anyway, every single time. The dust earns that reaction because of how it was made. Earth's sand gets tumbled smooth by wind and water, rounded over centuries until every edge wears away. The moon has neither wind nor water, so nothing has ever rounded its dust, ever, ground it down, or softened a single edge. Billions of years of micrometeorite impacts leave every grain sharp, jagged, and coated in glass, fine as face powder, yet cutting like broken glass under a microscope. Those same impacts melt and weld fragments together into composite grains called agglutinates, and locked into their glassy rims are microscopic flecks of pure metallic iron, a form of iron that does not exist naturally in any dust on Earth, thickest of all in the smallest, most dangerous grains, the ones a person is most likely to breathe. Size decides how far it travels into a body. Bulk grains run from about the size of coarse table salt down to fine flour, 40 to 800 micrometers, but anything under 20 micrometers counts as true dust. And the fraction that matters most clusters near 1/10 to 2/10 of a micrometer, about 50 times thinner than a human hair. Grains that fine do not stop in the nose or throat the way ordinary dust does. They travel straight down into the alveoli, the smallest, deepest branches of the lungs, the part of the body with no cough reflex able to reach it, and no way to clear it back out again. And it clings the moment it touches anything. Static charge and mechanical embedding fixed it to Apollo suits, boots, and tools within minutes of the first steps. And in lunar gravity, a stirred cloud of it drifted and resettled far slower than any dust cloud on Earth, closer to snow falling in perfectly still, windless air than anything a boot ever kicked up at home. It coated control panels inside the lunar module. Astronauts suspected correctly that it was coating their lungs the same way. Harrison Schmitt on Apollo 17 is the case still cited in the medical literature, sneezing and watery-eyed within minutes of repressurizing the cabin, describing the smell that clung to it as something close to spent gunpowder, a smell every crew after him reported as well. Mechanically, the dust behaved like a solvent poured directly onto the mission's engineering. It abraded straight through boot layers built from Kevlar-grade fabric, meant to survive years of wear. It defeated the knife-edge indium seals designed to keep sample containers airtight for museum-quality preservation, and it defeated them so completely that every single container brought back from the moon leaked. Not most of them, all of them. It scratched visors, jammed hinges, clogged bearings, and settled over radiators and solar panels until they lost their ability to shed heat or make power. That record, repeated across every single mission, is why NASA now calls it the single greatest hazard facing anyone who goes back to stay. But here's what the sneezing never told anyone. The mechanical damage was only ever the visible half of the problem. Lunar dust runs rich in silica and metal oxides, and its surfaces stay chemically reactive long after each bombardment by radiation. So its behavior inside the body tracks closer to the fine mineral dust that gives miners silicosis, a scarring lung disease built up over years of breathing exactly this kind of particle, than to any household nuisance. In 2018, researchers Caston and Dempel at Stony Brook ground lunar simulant down to a few micrometers and exposed it directly to human lung cells and mouse neurons growing in culture. The finest powder killed up to 9 in every 10 cells of both types. In the lung cells, the killing was so complete that researchers could not even measure the DNA damage sitting underneath it. In the neurons that survived, the DNA damage was there, and it was significant. In 2025, a NASA-led team ran a longer test, built to look past the first exposure to what lingers afterward. Rats breathed lunar dust, simulant 6 hours a day, 5 days a week, for 4 straight weeks, at a low dose and a high dose, then were tracked for 13 more weeks once the exposure stopped entirely. At the high dose, the lungs filled with the immune cells that signal ongoing injury, and the inflammatory chemistry driving that, a pair of signaling proteins called IL-1 beta and TNF-alpha that tell the immune system to keep attacking, stayed elevated through the entire 13-week follow-up. At the low dose, almost nothing changed. There may be a route further in still. Inhaled nanoparticles of other kinds are already known to travel from the lining of the nose up the olfactory nerve, the nerve that normally carries smell signals to the brain, bypassing the blood-brain barrier that ordinarily keeps foreign particles out of brain tissue entirely, a path confirmed in rodents for engineered particles, and suspected, though not yet directly shown, for lunar dust. Then came the twist that finally rewrote 50 years of assumption. In 2025, researchers exposed human immune cells to real dust carried home by Apollo 16, not simulant, the actual material astronauts once sneezed over. They found no true allergic response at all. No antibody signature of the kind a genuine allergy produces. Not an allergy, never was. What Apollo dismissed as hay fever was never the body reacting to a pollen-like irritant. It was cell death, inflammation, and DNA damage happening quietly the entire time, with no itch and no sneeze loud enough to announce any of it. And the second half of that twist matters just as much. The powder that killed 9 in 10 lung cells in the lab was ground from Earth rock, built to imitate the moon, not lunar material itself, and NASA's own scientists no longer trusted that substitute enough to set a safety limit from it alone. Testing had to go further, using pulverized dust the Apollo astronauts had actually carried home, because no Earth simulant could be trusted to stand in fully for the real thing. Physician Kim Prisk, who has studied the hazard closely, puts the practical danger into a single image. Particles about 50 times thinner than a human hair, capable of lodging in lung tissue for months at a time, with no dose low enough to call genuinely safe. NASA's own advisory group has only a preliminary limit to offer, about 0.3 of a milligram in every cubic meter of air, roughly a pinch of table salt dissolved through a small closet. And even that number sits inside an unsettled range running from 0.2 up to 0.7. No brush had solved this by 1972, and no SEAL had either. Every defense Apollo carried had already failed against grains too small to see with the naked eye, and the fix that would finally work on this would not look anything like a broom. The fix that finally worked did not look anything like a broom, and it did not look like a brush or a vacuum seal either. It looked like a field. Apollo's engineers had already tried the obvious tools, and each one failed for a specific, physical reason. Brushing did not just fail to clear the dust, it made the cling worse. The friction of bristle against grain built up a static charge, the same triboelectric effect that pulls a sock out of a dryer stuck to a shirt. And the more the dust was brushed, the harder it gripped. The vacuum seals fared no better, defeated again and again by grains only a few microns wide. Passive cleaning lost. Passive sealing lost too. Something else was needed. Something that could clear the dust without ever laying a hand on it. That something is called an electrodynamic dust shield, EDS for its short name. Charles Buhler, the engineer who now leads the lab behind it, has described lunar dust itself as a whole case of glass bottles smashed to bits inside a closet, then hit with a leaf blower. And EDS is built to answer exactly that kind of chaos without touching a single shard. It is a thin dielectric coating laid over a surface, with a fine electrode grid buried inside it, fed by a multi-phase, low-frequency alternating current. That current drives a traveling electric wave across the coating, and the wave lifts charged dust grains and carries them off the edge. No moving parts, nothing to jam, nothing to wear down over time. A broom built from a field instead of bristles. It has now done this on the moon itself, not just in a lab. On the 2nd March 2025, Firefly Aerospace's Blue Ghost Mission 1 touched down for the first fully successful commercial lunar landing, and across roughly 2 weeks of surface operations, ending around 16 March 2025, an EDS payload lifted real lunar regolith, clear off 2 test surfaces, a glass panel, and a thermal radiator. The images released afterward, as of April 2025, showed the same hardware-coated grey and then wiped clean. Vacuum chamber testing back on Earth, using simulated lunar soil, had already put a number on that clearing power, up to 99% of the dust removed, with separate reflectance studies confirming 96 to 99%, clearing all but 1 grain in 100. Apollo's brushes and seals never came within reach of a number like that. Not brushed clean and dusted again within minutes, wiped and kept clear. It is not a laboratory novelty rushed onto a single mission either. EDS has been in development for more than 18 years at NASA Kennedy's Electrostatics and Surface Physics Laboratory, long enough for a newborn to grow into an adult, championed first by physicist Carlos Calais for its first 15 years, and carried forward now by Buhler. It first left Earth in 2019, riding outside the International Space Station on an experiment called Missy 11, tested there across plain glass, a plastic called polyimide, and a prototype spacesuit fabric. Of 31 separate methods proposed for fighting lunar dust, as of the fall 2024 NASA roadmap, only 4 had reached the space demonstrated stage at all, and EDS sat furthest along of any of them. Because its electrodes can be woven directly into cloth rather than only bonded to rigid glass or metal, the same traveling wave can, in principle, protect spacesuit fabric boots, camera lenses, visors, and solar panels. Not only the flat test plates it proved itself on first, even a shield this effective is only the second layer of defense. Prevention still beats cleaning, so engineers are designing dust out of the habitat itself before it ever gets inside. NASA has studied 3 airlock architectures for a lunar base. A standard airlock cycles a crew member and a dust-covered suit through the same chamber together. A suit lock shares a bulkhead with the habitat instead, so the dusty suit stays outside its pressurized air entirely. A suit port goes further still, letting a crew member climb directly out of a suite mounted on the habitat's outer wall, stepping inside without the suit's dusty exterior ever crossing the threshold. A lunar airlock might cycle every other day for months at a stretch, so keeping the outside outside is not held in reserve as a backup. It is the primary defense. The stakes behind all of it were never abstract. Dust decides whether a base is still running on day 30 or has already failed by day 300. The difference between a mission that survives a single month and one that lasts the better part of a year. And once dust, like the cold and the dark before it, becomes a problem that can be designed around rather than merely endured, the question stops being whether a base can survive the moon at all. It becomes a question of who builds one first. Once the cold, the dark, and the dust are all, in principle, solvable, only one question is left standing, and it is no longer an engineering question. It is a political one. The United States has already picked its answer. NASA's Artemis program points straight at the same ice-rich South Pole this entire investigation has been circling. The same shadowed craters, the same sunlit ridges, the same 1,000-to-1 sliver of safe ground mapped sections ago. The goal is blunt. Put astronauts back on the moon for the first time since Apollo, in exactly the terrain already surveyed here, and this time build something that stays. For years, Artemis III carried a simple promise. The first crewed moon landing since Apollo 17, boots on the ground again after half a century of waiting. That promise did not survive contact with the calendar. As of February 2026, NASA restructured the mission so that it no longer touches the lunar surface at all. It becomes an orbital rendezvous and docking test instead. 4 astronauts riding Orion out to lunar orbit to dock with unlanded test versions of 2 competing landers, SpaceX's Starship and Blue Origin's Blue Moon, targeted for late 2027. Not a landing, a rehearsal for one. The actual first touchdown since 1972 now falls to Artemis IV, targeted for early 2028, still aimed at the South Pole region, as of mid-2026. The schedule slipped by an entire mission, and the slipping is itself part of the story this program keeps telling. The candidate ground has been narrowing right alongside the schedule. NASA named 13 candidate landing regions near the pole in August 2022, each a patch roughly 15 by 15 kilometers, all within 6 degrees of the pole itself. By October 2024, that list had shrunk to 9, names that meant nothing before this investigation, and now read like a map of everything already covered here. A peak near Cabeus B, Haworth, Malapert Massif, the Mons Mouton Plateau, and a second site called simply Mons Mouton, 2 rims named for Nobile and 1 for de Gerlache, and a stretch called Slater Plain. Whichever site is chosen, a crewed surface stay there is planned for only about 6 days, 5 3/4 to 6 1/4 days by NASA's own current estimate, as of October 2024. The rover meant to actually find the ice, rather than merely aim a crew at where it might be, very nearly did not survive to try. Viper, a prospector about the size of a golf cart, was built to spend 100 days working the shadowed craters, drilling a meter down with an instrument called Trident, and reading the soil with 3 separate spectrometers, work that would have produced the first real water resource map of the moon. It was fully built. It was fully tested. On the 17th of July 2024, NASA cancelled it anyway, after its cost grew from a $250 million baseline to about $609.6 million, judging it no longer worth finishing even with the hardware already sitting on the ground. Then it came back. On 19th September 2025, NASA awarded Blue Origin a task order worth up to $190 million to carry Viper to the South Pole aboard a Blue Moon Mark 1 lander, aiming for a landing in late 2027. Not stripped for parts after all, flying again on someone else's spacecraft. But the revival carries its own condition. The flight only happens if Blue Origin's lander first succeeds on its own maiden voyage, unproven as of this telling, and as of mid-2026, NASA was even weighing whether to send a different Mars rover testbed called Promise instead of Viper, or alongside it. A machine built once, cancelled once, and still waiting on somebody else's first attempt to go right before it ever leaves the ground, a second time. Not every open question inside the program is about hardware. Artemis Theku's pilot, Victor Glover, has said publicly that Artemis 4 should land nearer the equator first, rather than at the pole, warning that a stranded or incapacitated astronaut in the polar region could wait up to a week for rescue, far longer than anywhere closer to the equatorial supply lines. NASA has not adopted that argument, at least not as of 2026, and the plan still points south. Behind the scouting sits the larger plan. Artemis Base Camp calls for a foundation surface habitat, housing up to 4 astronauts for stays of a month or two, a pressurized rover, a second unpressurized terrain vehicle, power systems that may eventually include a small nuclear reactor, and hardware to manufacture oxygen and rocket propellant directly from the ground underfoot. Sources disagree on whether that permanent presence arrives by 2028 or drifts across the 2030s. That live-off-the-land technology is only half proven, and the half that works is not the half that matters most. NASA's own strategy runs on what it calls a leader-follower approach. Water ice extraction meant to lead the way, oxygen extraction from ordinary regolith meant to follow behind it. As of a 2026 review, the order has effectively reversed. Oxygen extraction is comparatively mature, tested repeatedly on the ground, the chemistry well understood, and the hardware already built. Water ice extraction has never been demonstrated on the moon at all, not once. A gap summed up bluntly in one review's own title: Lunar oxygen is ready, lunar water is not. A 2025 test at Kennedy Space Center processed 25 kilograms of simulated lunar highland soil, a load about the size of a full carry-on suitcase, over 36 hours, and produced oxygen matching predictions closely. On Earth, though, not on the moon, and not from ice, and not yet from the one resource this entire piece has been circling since the first section. The coalition behind all of it, at least, is not in question the way the hardware still is. As of 17th July 2026, 70 nations have signed the Artemis Accords, committing to principles that stay compliant with the older 1967 treaty governing space, transparency about what each program is doing, equipment built to work with everyone else's, and something called safety zones, drawn around active operations to keep separate landers and separate crews from colliding on the same crowded ridge. 70 governments, agreeing in principle to share a pole that has room, in practice, for only a handful of safe footholds beside the ice already mapped here, section by section. America is not running this course alone, and it is not running it first on every front. A second nation has been climbing toward the same ridges on its own timeline, with its own hardware already landed on the far side of the moon, gathering evidence this investigation has not yet touched. That second nation is China, and its path to the same ridges did not begin with a promise. It began with a landing already completed. On 3rd May 2024, Chang'e 6 launched for the far side of the moon, the hemisphere no human eye has ever watched rise over a horizon. It set down inside the Apollo Basin, itself nested within the far larger South Pole Aitken Basin, drilled, scooped, and sealed its haul, and on 25 June 2024 brought 1,935.3 grams of that soil home, the first sample return ever performed from the lunar far side. No other nation had ever pulled soil off that hidden hemisphere and flown it home intact. Basalt inside it dated to 2.83 billion years. Norite older still, close to 4.25 billion years. Rock old enough to remember the solar system's early violence. That was the opening move, a first bank before anyone else had even tried, and proof that China's hardware could already reach ground no other program had touched. The next one goes straight for the ice. Chang'e 7 is planned to launch on 24 August 2026, aimed at the illuminated southeast ridge of Shackleton Crater. The same crater this investigation has already mapped rim by rim and shadow by shadow. It carries 4 machines built to work as one: an orbiter, a lander, a rover, and something genuinely new, a rocket-propelled hopping probe. It can leap from sunlit ground straight down into a permanently shadowed floor, take its readings in the dark, and fire itself back up into the light before it runs cold. Picture a diver who can hold only one breath, surfacing to recharge before every plunge into water nobody has ever measured. Bolted to it is a single-purpose instrument, a water molecule and hydrogen isotope analyzer, built to confirm not just that ice sits there, but its form and its spread. One of 21 payloads the mission carries in total, 6 of them supplied by other countries. The mission is targeting a landing accuracy better than 100 meters, into ground where temperatures already run below minus 100 Celsius. As of August 2026, none of it has launched yet, and whether the hopping probe actually finds thick, concentrated ice near Shackleton, or only a trace of surface hydration, will not be known until it lands. Then comes the part no rover or probe can manage alone. Chang'e 8, planned for 2028, will test a solar-powered device that heats loose lunar soil to somewhere between 1400 and 1500 Celsius, hot enough to melt rock outright, and then prints that melt into bricks on the spot, not hauled up from Earth, grown from the ground underfoot. China has stated plainly what the experiment is rehearsing for: the technical groundwork for a base meant to stay. Built from the same regolith, this investigation has already spent an entire section describing as fluffy, fine, and abrasive. That base already has a name: the International Lunar Research Station, sited near the South Pole for the same ice every other program in this story is chasing, targets a basic version by 2035, though whether that basic version means a robotic outpost only, or one with people already living inside it, is not agreed across the sources describing it. The station is meant to grow in phases: robotic first, crewed later, mirroring the same sequence Chang'e 6, 7, and 8 are already rehearsing one mission at a time. It is not China's project alone. As of April 2025, 17 countries and organizations, together with more than 50 research institutions, had signed on. Russia and Belarus sit among them, and Pakistan is contributing a 30-kilogram rover riding along on Chang'e 8 itself. No count more recent than that April 2025 figure exists. So whether the coalition has grown larger since is simply not known yet. A separate track carries the astronauts. Built on the Long March 10 rocket, the Mengzhou crew spacecraft, and the Lanyu lander, China's human landing program is targeting a first crewed touchdown before 2030, as of 2026. The sequence calls for Mengzhou and Lanyu to meet first in lunar orbit. Then 2 astronauts descend inside Lanyu, while the cruise ship waits above for their return. A robotic campaign and a crewed one, running on separate clocks toward the same coordinates. Put together, the sequence reads like a checklist written years in advance: sample the ground, hunt the ice, print the bricks, land the crew, each step handed off to the next, while the schedule itself keeps moving. On paper, the coalition looks settled, with Russia named as China's senior partner in the whole venture, a founding signature on the very station this section just described. The ground told a different story. Russia's Lunar 25 lander, its first lunar mission since 1976, and its first ever attempt to reach the South Pole, tumbled into an uncontrolled orbit and crashed on 19 to 20 August 2023. The Lunar Reconnaissance Orbiter later photographed exactly what was left: a fresh 10-meter crater where a working spacecraft should have stood. Not a senior partner in practice, a name on a founding document and little else beside it. Days later, someone else reached that same pole instead. On 23rd August 2023, Chandrayaan-3 landed successfully near 69 degrees south, making India the fourth nation ever to land on the moon, and the first to do it anywhere in the South Polar region, having signed the Artemis Accords only 2 months earlier. Russia aimed for that ground and missed it entirely. India, aligned with the rival camp, simply arrived, and did it within the same week. Russia's own attempt ended as a crater on an orbiter's photograph. The symbolism was hard to miss. The nation named as China's senior partner failed to reach the pole at all, while a nation aligned with the opposing coalition got there first. Two credible programs, then, are converging on the same narrow set of ridges, on overlapping timelines. Each carries its own rockets, its own rovers, and its own coalition of partners into the same shadowed neighborhood this investigation has spent so long mapping. One runs on Orion, Starship, and Blue Moon, with a rover once cancelled and now flying again on someone else's lander. The other runs on Long March 10th, Mengzhou and Lanyu, with a hopping probe still years from its first attempt, and a partner list frozen at a count over a year old. Neither program is finished. Neither is even fully funded, tested, or flown, yet both are already aimed at the same handful of sunlit ridges beside the same buried ice. What happens when both actually reach that ground is no longer a question of hardware or physics. It is a question for whatever law, if any, still has something to say once somebody gets there first. That law, such as it is, dates back to 1967, the Outer Space Treaty, drafted at the height of the Cold War before anyone had confirmed a single molecule of lunar water, states in Article 2 that the moon and every other celestial body are not subject to national appropriation, not by claim of sovereignty, not by use or occupation, not by any other means. No nation may own so much as a plot of it. That sounds airtight. It is not. The treaty leaves the moon, what its own framers called the province of all mankind, and a province in this case with no court, no police, and no referee anywhere off Earth to enforce the rule. It never defines what counts as appropriation, and it draws no line at all between claiming a body outright and quietly extracting and selling what lies inside it. Not a loophole slipped in by accident. A gap left wide open on purpose, because in 1967 nobody drafting the treaty believed there was anything on the moon worth fighting over. 50 years later, that undefined gap is exactly what the ice race is now walking through. So what actually stops a nation, or a company acting on a nation's behalf, from behaving as though it owns the ground it stands on? Nothing in the treaty does. Not directly. Nations found the opening early. In 2015, the United States passed the Commercial Space Launch Competitiveness Act, recognizing a company's right to own resources it mines in space without ever claiming the ground beneath them. Split the ice, keep the water and the oxygen and the fuel, and the law says that belongs to whoever did the mining, whatever the treaty says about the ground itself. Luxembourg passed a nearly identical law in 2017, positioning itself as a small nation with an outsized stake in exactly this kind of ambiguity. Neither country asked permission, neither needed to. The treaty had left the door unlocked, and both walked straight through it. The Artemis Accords went further. First signed in 2020, they introduced something called a safety zone, a temporary area drawn around a nation's own operations that other parties are expected to coordinate with or simply avoid, justified as protection against collision and blast debris rather than as territory. It sounds procedural. Critics have pointed out for years that a safety zone drawn around an active mine starts to look a great deal like the appropriation Article 2 was written to forbid. And 5 years in, as of 2025, the signatories still have not defined how large a safety zone may be, how long one may stand, or what happens if two of them end up overlapping on the same ridge. The rival framework offers no more clarity. China and Russia's International Lunar Research Station was formalized by a memorandum in March 2021, with a partnership guide following that June, and it proposes a joint legal structure in place of safety zones, coordinated agreement among partners rather than a perimeter drawn by one nation alone. But as of the mid-2020s, it still has no completed resource rights framework of its own. Nothing spelling out who owns what is extracted or how a dispute between partners would even be settled. Two coalitions, two different vocabularies, and neither has actually answered the question both are racing toward. The rhetoric already carries the weight of that unanswered question. NASA Administrator Bill Nelson warned that the world must be very concerned that China could land on the moon and effectively declare it theirs, telling everyone else to stay out. And he drew the comparison directly to China's man-made island bases built on contested reefs in the Spratly Islands, outposts that asserted control on the ground long before any court settled who the reefs belonged to. China's foreign ministry called the comparison irresponsible and insisted its lunar ambitions were purely scientific. Neither side backed down from its framing, and neither offered a legal answer to the gap underneath it. Money explains why the rhetoric has an edge. Launching a single kilogram to the moon costs somewhere between $35,000 and $40,000, so every kilogram of propellant made from lunar ice instead of hauled up from Earth is money saved en masse, never launched at all. Multiply that across the thousands of kilograms a real mission needs, and the incentive stops being abstract. One recent campaign study found that lunar-derived propellant could cut the Earth launch mass of a recurring Mars campaign by roughly 68%, even after accounting for the weight of the mining hardware itself. That is not a rounding error. That is the difference between a program that strains a national budget for a decade and one that quietly becomes affordable enough to sustain. And here, at the very end, the whole investigation folds back into the idea it opened with. The moon has millions of square miles of surface. From orbit, it looks like room enough for anyone. But narrow the search to ground that combines near constant sunlight, safe footing for a landing craft, and a short walk to shadowed, ice-bearing terrain, and the number collapses to roughly 9 named candidate regions. Not a continent, not even a country. 9 named patches of ridge, most of them a few hundred meters wide, set against the far larger reach of shadow that has already been mapped, timed and measured across every section of this investigation. Some points along Shackleton's rim stay lit as much as 94% of the year, sitting directly beside the densest ice found anywhere at either pole. Layer the scarcity and the shape of the whole story becomes visible at once. The resource itself was scarce. Hundreds of millions of tons sounds enormous until it is measured against an entire world. The safe ground beside it was scarcer still, outnumbered by the surrounding shadow by roughly 1,000 to 1. And now the third layer closes the story. The number of places where a real, permanent foothold can actually stand, lit, stable, and within reach of the ice is scarcer than either of the layers beneath it. 3 tiers, each narrower than the one before, and the narrowest of all is the one that will actually decide who gets there. That scarcity is precisely why first arrival works as a claim, without ever needing to be one. With only a handful of viable corridors on the entire moon, whoever plants the first working base forces every later arrival to build around it, to negotiate around it, to route their own missions around ground already occupied. No treaty is broken. No flag changes anything on paper. Not a claim on paper. A claim in practice, which turns out to be the only kind that matters when the ground itself is this scarce. The best ground is simply taken quietly, and by the time anyone asks whether that was legal, it is already the ground everyone else has to work beside. 2 coalitions are still years from finishing what they have started. Their rockets are unproven, their rovers are cancelled or delayed or contingent on a rival's first flight succeeding, and their legal frameworks remain exactly as undefined as they were the day each was signed. Neither has settled how large a safety zone may be, how long one may stand, or what happens the day 2 of them meet on the same narrow ridge. Nobody has ruled on whether an indefinitely maintained perimeter around a working mine is legally any different from the appropriation the treaty was written to forbid. But the ridges are not waiting for any of that to resolve. The ice has sat there, patient and untouched, for well over 1 billion years, preserved by the same cold and the same darkness that will make it so hard to reach. Whoever stands on that ground first will not need to say the word claimed. The ground itself will already have answered the only question that was ever really being asked, and it will keep answering it for whoever arrives next, long after any court gets around to weighing in,